Now we proceed to question 3 or revision 3, which is on vector calculus. That is the gradient, the divergence, and the curl. So we have our first question, which is on gradient, and then we calculate the directional derivative of our gradient, and then we proceed. Now, before we start, we need something. We know that the nabla, which is this, is simply given by d or dx plus d over dy plus d over dz. So this is something that you should always remember for this. That is our nabla. Now the gradient, now we go to what we asked, the gradient, which is our nabla operator, times our phi, which is a scalar field, will simply be d phi over dx, the partial derivative of phi with respect to x, then d, and that will be I, because when you find the gradient, you get the vector. So the gradient acts on the scalar field to give you a vector. In fact, that is what we should know. The gradient acts on a scalar field to give you a vector. So that is I, then d phi over dy j, then plus d phi over dz k. So the gradient operates on the scalar field and gives you a vector field. So let's start by solving for each part, and then we put it on our equation. So let's start with d phi over dx, and that is I. This will be d over dx. Now our phi was given to be x squared y cubed plus y z squared. So we are going to differentiate that with respect to x, and then this will be I. We are going to differentiate again phi partially with respect to y, so that will be d over dy into the same thing, x squared y cubed plus y z squared, and this is j. Then finally we'll do d phi over dz for k, which is the same as this is for j, I forgot there, which is d over dz into bracket our phi is x square y cubed plus y z square k. Okay, so let's see. Now we need to differentiate our phi with respect to x. So it means where x is missing is a constant, and differentiating a constant is 0. So we only observed x in our equation. So in the first term, x is squared. We don't touch y because we are differentiating with respect to x. Now using a power law says that if y equals to x power n, then dy over dx is equals to n x power n minus 1. So our power of x is 2, so first we multiply by 2, then we go to x, we less its power by 1, so 2 minus 1 is 1, we don't need to write 1. Then y remain y cubed. Now on the second part, you can see we don't have x here, so differentiating this part is 0. So here we only observed this. And when the power is 2, 2 comes here, multiply x, and then 2 minus 1 is 1. So that is why we have only x power 1. And y cube retain because y is not x, so we don't touch it. So that is what we call partial derivative. You only differentiate with respect to what you have down here. Now in the second case, we want to differentiate the scalar field here with respect to y. So we only look for y, where y is missing is a constant, that means 0. Now in the first term, we have y here, which is power 3. Now y, first of all, because of power 3, we multiply by 3. X we don't touch, but now the power of y reduces by 1. So first multiply by 3, then less 1, so it will be 2. The next part we have y again, so we'll continue. Y is power 1. 1 times everything is the same thing. When you less 1 minus 1, this part becomes 0. So it is 1 minus 1, which is now 0. Any number raised by 0 is 1. So we only remain with z on the second term after differentiating, because y, you multiply by 1, then less 1. Any number raised by 0 is 1, so only z remains there. Now we differentiate, and the last term, the last part, we are now differentiating with respect to z, partial derivative. On the first term, there is no z, so it is 0. On the second term, we have z squared, so 2 times the whole thing first, we get 2, and then z, the power of z, okay, y we don't touch because it is not z, so we write it the way it is. Then z reduces, the power reduces by 1, so 2 minus 1 here is equals to 1. Here 3 minus 1 is equals to 2. Now that is why we remain with z alone. And remember, the whole of this is j, the whole of this is I, and the whole of this is k. Good. So that is what we have. Now your answer, which is nabla, or the gradient of phi, is simply the combination of all of them. The first part is 2x y cube I plus 3x square y squared plus z squared. All of this j, then plus the last part is 2yz, and that is k. Maybe I can just push this down a bit well for you. So our number phi, which is our gradient, is 2x y cube I, then plus into bracket 3x square y squared plus z square, close the bracket, j, then plus 2yz k. So that is our vector we obtain when we operate on a scalar field. So the gradient operate on a scalar field to give us a vector field. So that is what we have for our first question. It is Roman 1. Now in Roman 2, you are asked to calculate the directional derivative of the scalar at the point P in the direction of the vector v2i minus j plus 2k. Now first, let's evaluate the gradient at the points. So we are going to evaluate our gradient at the points 1, -2, 1. So means if you look at here, this is our x, this is our y, and this is z. So let's substitute. Our gradient is 2. Okay, let me use black to ensure everything is okay. So we have 2 times x, which is 1, times y cube, which is -2 cube, that is I, then plus 3 into x square. So we are having x is 1 square, then y is -2 square, then plus z, which is 1 square. All of this is j. Then plus, the last part is 2 into y -2, then z 1, and this is k. So when you work out for the gradient at this point, you get 2 times -8 is -16i. So that is what we are going to have. Okay, let's see if we have a plus there. Of course we have. Now 3 times 1 is 3 times 4 gives us 12. Plus 1 gives us 13j. We have 3 times 4, 12 plus 1, 13j. Then the last part we have a negative. 2 times -2 give you 4 times 1 is -4. So we have our gradient at the points that we were told. Now next, let's calculate the unit vector v in the direction of vector v. By definition, the unit vector v is simply the vector v divided by its magnitude. That is the definition of a unit vector. Vector v divided by its magnitude. So let's find v magnitude first. This will be the square root of our v. X squared is 2 squared plus y is -1 squared because it is -j, then plus k, which is 2 squared. So once we get the magnitude, we can put it in the definition. So this will be square root of 2 squared is 4, 4 plus 1, 5, 5 plus 2, 7. So the magnitude is 7. Put again 4, 4 plus 4, no. 2 squared is 4, 4 plus 1 is 5, 5 plus 2, 9. Sorry. Now the magnitude of the square root of 9 is 3. Now, the unit vector v will be the vector itself, which is 2i minus j plus 2k. The whole of this you divide by 3, which is the magnitude. If you do that, you have a common denominator, so it is 2 over 3i minus 1 over 3j plus 2 over 3k, because it is a common denominator. Now, we proceed. So we were asked, let me put this down. We were asked to calculate the directional derivative of phi at the point where we have p1, -2, 1 in the direction of this. So we define that, that is the next thing, the direction of the derivative on this vector v for our phi gradient is simply given by our gradient, which is phi times our unit vector, the dot product of our phi gradient times the dot product of our phi gradient and the unit vector, which is in this direction. So how do we do that? Our phi has, remember in dot product, we have row and then by column. So our row will be our gradient. So what is our gradient? I'll go up. Our gradient is -16 for x, 13 for y, and -4. Then our unit vector is 2 over 3 for x, -1/3 for y, and 2 over 3 for z. Now what do we do in this case? You now need to multiply x by x. Remember, i's and j's disappear in the dot product, then y, and then finally z and z. So let's do that. -6, -16 times 2 over 3, and then 13 times -1/3, and then -4 times 2 over 3. So when you do this particular math, you get -32 over 3 plus -13 over 3 plus -4 8/3. So calculator can help us solve this kind of problem. So let me proceed to my calculator and see what I have. And since the base is the same, then we can now work on the top. So -32 plus -13 is -45, plus -8 is -53. That was just simple like that. So that is the answer. So the direction derivative is -53/3. That's how we solve such kind of problem. Now, we're going to the next question, which is B. We have solved for A. Let's see what is in B. A vector field is given by this. Calculate the divergence. So divergence act on a vector field to give us a scalar. So this will give us a scalar. When divergence of the vector is the output of the divergence of a vector is a scalar. So how do we define this? This one is defined by d/dx f of x plus df of y over dy plus df of z over dz. So that is how we define the divergence. So the divergence operates on the vector field to give us a scalar. And this is given by d/dx fx, dfy over dy plus dfz over dz. So from our information we have here, we can see clearly from the equation we are given, fx is the coefficient of f in the direction of x, which is x squared z. Then fy is the value of f in the direction of y, which is -2 y cubed z squared. Then finally, fz is given by x y squared z. Good. You're proceeding well. So we are going to find d/dx of fx, which is x squared z. Remember, in the divergence operate on the vector to give us scalar. So these are dot products. So I dot I, j dot j, k dot k is equals to 1. So we don't have i's and j's and k's in the result. So when we do this, now we observe x. We don't look z. Power is 2. We multiply by power first using power rule. Then we less 1, and then we have z. Now we want d/dy for fy. Fy is -2 y cubed z squared. Again, we observed only y. So -2, 3 will come here. 3 times -2 become -6. Then y will less 1, we have 2, and z remain the same. Now the next part is d/dz of our fz, and fz is x z. Fx y squared z. Now we observe z, so means we leave x alone and we leave y alone. Z is power 1, multiply everything, it remains the same thing. Less 1 minus 1, you get z power 0, which is just 1. So now this is what we have. So the gradient, so the gradient will give us a scalar, which is, we can put them together, 2xz plus, not plus but minus, because it is minus. So 2xz minus 6 y squared z squared, then plus x y squared. So that is our scalar that comes after we find the divergence of f. So the divergence operate on the vector and you get the output as the scalar. So it's just the dot product. Now we move to Roman 2 of that question. Roman 2, we are asked to find the curl. So the curl acts on a vector and you get a vector. So it's a cross product. So the curl is defined like this. So the curl of the vector will act on a vector to get another vector. So how do we define this? The cross product is given by the determinant. So we have I. Okay, let me just put green the way I used to. So to get the cross product, remember our tactic was to use the determinant method. So we have our I, we have our J, and we have our K. Now our curl, you know, our nabla here is D over dx, then D over dy, then D over dz. Our F is Fx, and then Fy, and then Fz. Good. Now let's now continue and put the values. So we have to put that again. Sorry about that, but that is what we want. So I, J, K. This remain D over dx, D over dy, D over dz. Now fx, from the equation we were given, we have them. Fx is x squared z. So fx is x squared z. No, we put y. So x squared z. Then fy, negative 2 y cubed z squared. So fy is negative 2 y cubed z squared. I might remove this to give me a space. Then negative 2 y cubed z squared, negative 2 y cubed z squared. Then fz is x y squared z. So we have x y squared z. Now I can have my line there. And if this look bad, I can move this to here. So d over dz, and I move k here. And I can wrap this one. I can also switch this one to the center position. So we have j, which is d over dy. Now the trick is the same. The way we deal with a dot product, a cross product is the same way here. So we need three matrices. The first matrix is for I. Remember J is negative. Remembering our Cartesian coordinate system, when you cross from I to K, it is a reverse, which is negative J, while K remain positive, because when you cross a J, I to J, you get K. Now the same trick, you want I, this one, okay. Same trick, you want I, you delete that. So if you delete that, the matrix formed is D over dy, if you can see, D over dz, then we have negative 2 y cubed z squared, then we have x y squared z. Now let's go to j. When you want j, as usual, we delete j. When we do that, we remain with d over dx and d over dz. Okay, I'm moving on. Then we have d over dx, d over dz. Then we have x squared z. Then we have x, y squared z. Good. Now we go to the last part. Now the last part we want k, so we delete k. The matrix that we have there is d over dx, and then d over dy, d over dx, d over dy. And we have x squared z. Then we have negative 2 y cube z. Now our next step is to find the determinant. Main diagonal minus other. Main diagonal minus other. Main diagonal minus other. So we need 3 brackets. The first bracket is for I minus the second bracket is for j plus the second bracket is for k. Okay, so let's do. So it will be d over dy into x y squared z minus d over dz into negative 2 y cube z squared. Okay, that is for I. And then let's move for next to d over dx, d over dx into x y squared z minus d over dz into x squared z. So cross multiplying d over dz x squared z. Then k d over dx, make sure we are correct, into, making sure, negative 2 y cube z, then close the bracket, minus d over dy into x squared z. Now that is what we are going to do. Now let's work out the derivative. Differentiating this with respect to y, you only look at y. When you do that, so we need another bracket, big one. Then we have I. So when we do that, now dy on this, y will become now 2x y z minus y, because you are only checking y. Now 2 will multiply x, and then you less 1 from y squared, and then z remain intact, minus become positive. Now 2, you are now differentiating with respect to z, means you only look at z. Z is squared. 2 times 2 is 4. Y remain untouched, and you less the power of z by 1. So it will be 4 cube z1 minus. That is what we have. Now minus, we need another one here. For j. And we need here for k. Let's proceed. Now we only look x, d over dx. X will disappear because it's power 1. So we only remain with y squared z minus. Here you differentiate with respect to z. X squared will remain, z disappear, because we only have z power 1. So when you multiply by 1 less 1, z become power 0. Okay, so we are moving well. The last part over dx, you look here, we have negative. Now you are differentiating with respect to x. We don't have x in this term, so it is just 0. There's no need of even negative. Differentiating a constant is 0. Then minus, because there is no x in this term. With respect to y, there is no x again in this term, so minus 0. So there is no y in this term. You differentiate a constant, you get 0. There's no x in this term. You differentiate a constant, you get 0. So k vanish. So what are we remaining with as our curl? So our curl, which is this, cos our field, vector field, is given by 2x, y, z plus 4y cube z, and this one will be I, then minus into bracket y squared z minus x squared, and that one is j, and k disappear. So that is our curl. Now, once we have our curl, we were told to evaluate the curl of f at a point. So we have our curl. Now we want to evaluate our curl of the vector field f, which should give us the vector. We evaluate it at a certain point, and the point is 1, 1, 1. So we have 1, 1, 1. So of course, you know what this means. It means this is x is equals to 1, y is equals to 1, z is equals to 1. So when you evaluate our curl, we are going to have 2 times 1 times 1 times 1, because all of them are 1, plus 4 times 1 cube times 1. And remember, this one is all going to be I. Then minus into bracket 1 squared times 1 minus 1 squared, then all will be j. When you work this out, our curl will be 2, then 4. 2 plus 4 is 6i. Then when you check here, you check carefully, we have 1 minus 1 is 0, so j disappear again. So our curl at that point is simply 6i. Good. So that is how we get that. 6i. Now the next question is a statement. State whether the vector f is rotational or irrotational at point Q. So at point P, at point Q, sorry, the curl is equals to 6i, which is not equals to 0. Now, if it is not equal to 0, we say it is rotational. Hence rotational. Maybe I say hence rotational. But because you need to understand this, if this, don't need for this, we have already answered our question. If this is equals to 0, then we say irrotational. So since ours is not 0, the correct answer is rotational. This is just for the purpose of notes. Okay, last question. A force field acting on a particle is given by the equation. Prove that F is a conservative force. F is a conservative force if the curl of F is 0. Yeah, so we need to confirm if the curl of F here is 0. Now curl means the cross product. So I, we have already performed that. J, we need I first is d over dx, and f of x, which is on the I, will be 2x y plus z cube. Then j is d over dy, and f of y is x squared. Then k is d over dz, and f of z is 3x z squared. Good, we are done. Now we need to extract our three matrices. So one will be for I minus, because j is negative, we have already proved that. Next will be for j, and then plus the last matrix we want is for k. Correct. So as usual, we want I, we close I. When you close I, the matrix is D over dy, D over dz, and then we have x squared, then 3x z squared. Now you want j, you close j, then when you want j, the matrix remaining is D over dx and D over dz, then you have 2xy plus z cube, and then 3xz squared. We want k. So to get k, we close k. When we do that, the matrix that remains is D over dx and D over dy. So D over dx is 2xy plus z cubed. D over dy is x squared. Now let's get the cross product. Now the determinant, sorry. So the determinant is main diagonal minus the other, main diagonal minus the other, main diagonal minus the other. So we have that for I. Let's have it. D over dy into 3xz squared minus D over dz into x squared. That is for y. For I. So I'll close this and put I. Now for z, I'll have D over dx into 3x squared z, then minus D over dz into 2xy plus z cubed. Okay, I will close and then say, I will close and then say that is j. Now plus, let me have my k here because of space. Now k will be D over dx into x squared, then minus D over dy into 2xy plus z cubed. Close your bracket, and that is k. Now let me work out one by one. Now in the first case, you have dy over d over dy. You look for y here. Let me just have that. You look for y, there is no y, so that is 0. Since there is no y here, differentiating a constant is 0 because there is no variable y here. Minus d over dz, there is no z here, again differentiating a constant is 0. So this gives me I, so I is that. Then let's have j. Okay, now j, d over dx, we have x here. Of course, this will be 6. 2 times 3, 6. Then x, z remain untouched. Minus d over dz, here again, we have 0 here. Why do we have 0? Because z is not in the first term. So the first term is 0. I hope we are correct. Let me just go here and then look at it. 2xy plus z cubed. So 2 d over dy, if you want I, That's fine. So when you want j, you do d over dx. If you want the d over dx times 3 d over dx, then d over dz. This 2xy plus z cubed, then 3x z squared, 3x z squared. So d over dx of 3x squared z, then d over dz of this. Okay, when you want, think that's okay, 3x z squared. When you want k, I'm counter checking. So when you want k, then d over dx, d over dy, 2xy z cubed, then x squared. So we are now differentiating this part where we have dx times this, dx of 3x squared z. Okay, 3x squared z. And let me check the force is 3x z squared. I just see the mistake. 3x z squared and 3x z squared. So this is where the problem is here. So this is squared, x is not. Remember we were told to prove if it's a conservative force. So I'll just rub this and repeat j. Let's come up. J is here. So we pick dx, 3xz squared. 3xz squared. Okay, so let's continue. Now d over dx, 3xz squared is 3z squared minus d over dz. This part is 0, this part becomes, what do we get here? And let me check again, counter check. This is 0, yes, so we have 3. Then we less the power of z by 1, so 3z squared. I think that's fine. Yeah. So plus on k, we have to be very keen while working with this because any confusion. For k, this one, if you differentiate x squared, then it will be 2x minus. Here, with respect to y disappear, you remain with 2x. Why? Because this has no y, so it is 0. This one, this disappears, so 2x. Here, 3 comes here, you less 1, and here 0 because there is no z. Here, 1, you are looking for 1 on x, then it become here. So 1 come here, x become power 0, it disappears, so 3 times z. Good. So what do we have at the end? So we have 0i plus minus 0j, then plus 0k, which is 0. So since the cross of f is equals to 0, then we can say f is conservative force. Good. So that is the end of revision 3. Revision 3, which is on vector calculus, was long, but it works. So you have the end result is F is a conservative force because the cross product is 0.